Okay, nerds. Today we are going to we're gonna put a bow on this lesson. This is it, the last day. I can't take it anymore. Okay, we've stretched it out across 4 days, and we might not even get to all the examples in the lesson. To be real with you, it doesn't matter. Okay, you're going to have learned enough to be ready for the test review and test. What you're going to need to work on more than likely is speed, because these questions take time. This one in particular, you notice how much space I gave you? Yeah, it's gonna be filled. Please don't write large, okay? How many of these are on your test? One. Only one that requires this much effort, okay? All the other ones can happen with faster methods. But in this question, we've been told to find the zeros and sketch this graph. Yesterday, remember, we talked about multiplicities and how it makes graphs behave. So if we could factor this thing, we'll be able to see the multiplicities of its roots, and we'll be able to see said roots, and we can see the end behavior right now. Since the end goal is to sketch the graph, let's talk about end behavior. And I'll just, I just draw it up here, I guess. The degree of this polynomial is even. What does that tell? It's a degree 4. What does that tell me about the endings? That they're the same. So these two endings are either both up or both down. And since it starts with a negative, what do we know about them? They're both down. Yeah, so I'll draw that in yellow. It'll probably be the only yellow I use today. But the endings for this graph are both down because it is an even degree polynomial, degree 4, and because the front number is negative and negative people front. Okay, there. So we'll set the yellow aside. We'll retire the yellow for the remainder of the lesson. Finding all the zeros requires us to factor. And when you're factoring, what's always your very first step? GCF. Yeah, we got to look for that GCF. This one has one. The GCF happens to be -2. Why negative? Because the front term is negative. Yes. So dividing everything by -2 is going to give me x to the 4th plus x to the 3rd minus 7x squared. Help. Minus 13x minus 6. I didn't goof up any symbols, did I? No. Dividing by negative changes them all. There it is. Alrighty. So you have 5 terms. So clearly factoring by grouping is not going to be an option. Okay. And we've already removed all of our GCFs that we can. What we have left here is a 4th degree polynomial that ends with a -6. We do our P over Q, our rational root theorem, using this polynomial. The -2 will not affect our solutions. So from now on, I'm trying to factor this. And at the very end, I'll just make sure there's a -2 written on the front. So when I'm doing my remainder theorem, I'm doing this. When I'm doing my synthetic division, I'm doing this. Cool? I'm no longer looking up here. This has done everything it can for me. It showed me my end behavior, and it showed me my GCF. This is where we live now. So our P over Q is using the factors of 6 as P, and the factors of 1 as Q. Okay, well, the factors of 1 is easy. That's just 1. We like when P over Q is over 1. Makes life easy, right? So the numbers we can divide 6 by, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. I try to stay away from what I would consider mean numbers when I have you do these by hand. Like, bless you, like the number 24, that number's mean because it's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 24. So I would stay away from something like that because it's just a mean number. When I have you do these, don't worry, it'll typically give you 4 options like this or less. You know, like I'll stick to numbers like 6s or 10s or 14s. Things that can only, like 2 numbers will go into and that's it, other than 1 in themselves. Because I don't have a reason to beat you up with a billion options. Alrighty, now, Descartes' rule of sign, again, is one of those tools where it might be useful to us. It might be. So if you take a peekaboo at it and look at, this is f of positive x, and again, Descartes will assign here, we're not thinking about this. If you look at f of positive x, the number of sign switches it has will tell you something about the number of positive real solutions. And the sign switching happens only one time, right here. This tells me there is one positive real solution because there's only one sign switch on f of positive x. Think of this as being f of positive x because I didn't plug in negative x. So we know there is one positive real solution. If we were to plug in negative x, I'm not going to actually write it down. This would stay positive. This would switch to negative. Then this is negative. That's one sign switch. This switches to positive. That's two sign switches. This switch and this stays negative. That's three sign switches. So if I were to do f of negative x, I have three sign switches. So that's 3 or 1. It really didn't do much for us. This is really the only thing that could do anything for us. And the only reason it would be any helpful to us at all is if, let's just say, you know, I'm going to check negative 1 or positive 1 with my remainder theorem. If positive 1 works, I'd be thrilled because I would have found my one positive real solution and I could discount all the other positives. I'm going to be honest with you because I've already done this question today. I already know Descartes' rule of sign, it doesn't help us at all in this question. Okay. Unfortunately, it doesn't help at all in this question. But, you know, you win some, you lose some. It's not a big deal. Remainder theorem time. Let's start checking numbers. The easiest number to check is always going to be positive 1. And again, I'm looking here, not to the original. One, 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 one. There it is. Okay. And we hope, remember, we're trying to get a 0. Trying to get a 0. One plus 1 minus 7 minus 13 minus 6. Okay, there's no way that 2 minus all these numbers equals 0. I mean, I don't know what it is. I just know it's not 0, and that's all I care about. I'm trying to get a remainder of 0 so I can find a factor slash solution. Then I always go for the next biggest number, negative 1. And we really hope that this works. Otherwise, we have to check a third number. This is like fancy guess and check. Negative 1 to the 4th is positive 1. Oh, but then I got a minus 1. All right, well, we're at 0 so far. Then squaring that gets me back positive, so minus 7. So now I'm at negative 7 plus 13. Uh-oh, negative 7 plus 13 is 6. Got him. We found a solution, which means we also found a factor. Since x minus 1 is a solution, we know that x plus 1 is a factor. And that's a big deal, because if you can recall from yesterday, I'm just going to flip this over for a second. We graph from our factored forms so we can see multiplicities. So we are going to need to factor this thing. I found a solution. Every example that you've seen me do so far with these, I've done synthetic division once I had a solution, right? But that was because all the other examples, there we go, I can speak, that we've done so far were cubics. And if you perform division on a cubic using a linear, the result is a quadratic. We could solve quadratics very simply, either by factoring or the quadratic formula. This, however, is a 4th degree polynomial. So in order to get this down to a quadratic, I need to find 2 of its solutions. I have only found 1 of them. So we're not done hunting. We still need to find another solution. Is everybody clear with why I need 2 of them this time? One person shook their head. Just for example, if this was a 5th degree polynomial, I would need to have found 3 of them so I could get myself down to a quadratic that I could handle. The only time we can handle cubics is if they factor by grouping. I'm not going to lie. If we do synthetic division with this number, we might end up with a cubic that factors by grouping, or we might not. So is it worth the effort to check? I mean, that's a personal choice. I don't like to bother unless I know it's going to work, so I just choose to keep going with my remainder theorems. X to the 3rd style graph. Because all the things that you've seen factor by grouping were x to the 3rd or larger. Because you have to have even terms, so 4 terms or 6 terms or 8 terms. So it would be x to the 3, 2, 1, none. So if it was a cubic and the coefficients matched, then you might be able to factor, then you'd be able to factor by grouping. But I can't guarantee that's going to work, and because I can't guarantee it, I'm not even going to bother trying. I don't like to do extra work. Yes, exactly. So we're going to find a second solution, and we'll do synthetic division twice. Yep, it's exactly what we do. And you'll have to do that in the homework on the bottom of the first page because it's a 4th degree, and I didn't give you any of its answers. Okay? All right. Now, let's go ahead and check the next smallest number, which would be positive 2. I will never say that these questions are fast, because they are not. And that's why I only put 1 on your test. You'll need to focus on being speedy. Make sure that you know how to do regular factoring and special case factoring and factoring by grouping. That way when you get to one of these monsters, because there's only 1, it doesn't take half your test time. Okay? Let's see what we get. 2 to the 4th is 16. Plus 2 to the 3rd, which is 8. I'm up to 24. Minus, this is negative 28. Then minus 26. Then minus 6. Okay. No way that's 0. Because this is only going to add to 24, and 2 of these negative numbers are bigger than that. So that didn't work. My space is at a premium, isn't it? Still on the hunt for one more solution. Next number to check is, and you notice we still haven't found that positive real solution that Descartes' rule of sign said we have. No guarantee it's pretty. That's why. The next number would be negative 2. I'm just going to keep scooting left and hope that it gets less and less tight on the right side. Drop a negative 2 in. Whew. These things really do take some mental fortitude. Like, don't give up, okay? Negative 2 to the 4th is positive 16 again. But this time it's minus 8. This is going to be 28, negative 28 again, because I'm squaring that negative 2, so it doesn't matter. But this time it's plus 26, and then minus 6. 16 minus 8 is 8. 8 minus 28 is negative 20. Negative 20 plus 26 is 6, and 6 minus 6 is 0. Thank goodness we found it. The second solution, x equals negative 2, which means we also know a second factor, x plus 2. All right, we have 2 solutions. That means we can do synthetic division twice now. Let's make sure we're not missing any terms. X to the 4, 3, 2, 1, none. I'm not missing any terms. Remember, if you're missing a term, you have to hold it open with a 0, even if you're doing synthetic division. Doesn't matter. Okay. There's the coefficients of the polynomial that I'm trying to factor. We already know that we're going to get 0 as a remainder when we plug in -1. We already know that. Drop your 1 down. -1 times 1 is -1, and adding straight down gets me a 0. -1 times 0 is 0, adding straight down, -7. -1 times -7, +7. Adding straight down gets me the 6. That way I can multiply and get -6. And you know what? That would not have factored by grouping. The only way that you're going to be able to factor by grouping is when you do your synthetic division, if your 4 terms, if they oscillate between numbers like 1, 2, 1, 2, or 2 minus 5, 2 minus 5. Thank you. So it doesn't factor by grouping. Like I said, I'm glad I didn't waste my time trying. This is a cubic. This is x to the 3rd minus 7x minus 6. The good news is we found a secondary solution at x equals -2. So we're going to perform our synthetic division at this level now. We get to drop the 1 down and go through the whole process again. So -2 times 1 gets me -2. Adding straight down gets me -2. -2 times -2 gets me +4. -7 plus 4 is -3. Multiplying those two negatives does get me the +6 that I needed. And this is a quadratic. Why did I do synthetic division here? So imagine I asked you to factor the number 128. Okay? So instead of a polynomial, we just got a big number, and I'm asking you to factor it. And I told you that, or you found out that 2 goes into it, and so does the number, I don't know, 16. And I wanted you to keep factoring. Would you have done this? If I said continue to factor it? You wouldn't have, would you? You would have divided by 2, and then the result, you had divided that by 16, correct? That's why. So it's almost like we did division. We did division twice. We divided by the first linear term, and then we took our result and we divided it by the next linear term. The same way that you would have done this number divided by 2 and then divided by 16 to break it down to get to the number 4. It's the same idea. It's dividing by 2 different numbers. So here's the thing. You found out through the remainder theorem that they were both factors, which means yes, you'll always be able to divide by both of them because they're both factors. Yes, Max? And that is a fantastic question that someone in first period asked the same question. No, order does not matter because, like if I give you this number, 128 divided by 2 is 64, divided by 16 is the number 4, right? But 128 divided by 16 is 8, and 8 divided by 2 is 4 again. So no, order of multiplication, Order of division, unimportant. So nope, whichever order you care to do them in. We good? Those are good questions. So this is a quadratic. This is x squared minus 2x minus 3. Does this factor? Are there two numbers that multiply to negative 3 that add to negative 2? Negative 3 and positive 1. Guess what? We have completely factored our original polynomial. These two things are factors. And if you come back up to the remainder theorem, these two things are factors. Max? Ah. Yes, so Max has realized that x plus 1 showed up twice. So, by the way, that's pin on my finger. So when you go to write this thing completely factored, f of x equals. What's the very first thing you need to write? Negative 2. Please don't lose your GCF. And because the order of multiplication doesn't matter, the order that you write these factors doesn't matter. The first one we found was x plus 1. But it showed up in two places, so it's squared. Then we found an x plus 2, and we also ended up with an x minus 3. So that is our f of x completely factored. This shows us our multiplicity, and we've already determined our end behavior, and it shows us our three unique solutions. Now we're ready to graph. Wow. We had three solutions. Remainder theorem found us negative 1, but because it showed up twice, because there's an exponent of 2, what's going to happen at x equals negative 1? There will be a bounce. Our graph will bounce off the x-axis. Remainder theorem showed us negative 2 is a solution. And the final factorization showed us that positive 3 is also a solution. And these two factors do not have exponents, so they are of multiplicity 1. So we will cross through our x-axis like a line, because that's a power 1 graph for both of them. So at long last, we're ready to actually graph. It's like a 10-minute question. So if you're the kind of person that doesn't do the work honestly in the way they're supposed to, you're going to be the kind of person running out of time on the test. So make sure that you're actually doing the practice the way you should. Now, I had someone in first period ask me a question, and I think it's pertinent to this example. Out here, there is not an x. That means there is not a solution out here. Solutions only occur where we have x's. Can't lose this GCF. It's part of the factorization, but it has no bearing on what the solutions are. Cool? Okay. So we have solutions at negative 1, negative 2, and positive 3. So 1, 2, 3. I'm trying to draw my x-axis to scale. Like that. And now it's time to graph. I'll graph in red. We know our endings point down. And I go from left to right. So right here at negative 2, I need to cross through the x-axis without getting wiggly. There, I crossed through without being wiggly. The next time I interact with the x-axis is at negative 1. So clearly I'm going to have to come back down. But what happens at negative 1? I bounce off the x-axis. So come back down and boink, like that. Bounce off the x-axis. I can't go up forever. I'm clearly going to have to come back down to x equals 3. And you can see I'm going to cross right there. So Something like that. How far up do I take the bump? I don't know, as far as you want. Essentially, the closer they are together, the smaller the bump. The further away they are from each other, the bigger the bump. That's basically how it works. But at least you have a general idea of what this fourth degree polynomial looks like. Pretty neat, huh? On your test, you have this question is multiple choice. And it says which of these could be the graph. And you'll have to factor it in order to figure out which one is the graph. And none of the graphs have values on the y-axis, just like this. Okay? So it's the x and the behavior. So in behavior, the zeros and the bouncing crossing behavior that decides what the answer is. Are you comfortable with all of those things? If you're not, say something to me. Yes? Okay, that's all the skills wrapped into one question. The only thing this question didn't have was a special case or factoring by grouping, but it had everything else that we've done for polynomials since last chapter. That's a big boy. Next is something that we have talked about before, but I'm going to bring it up again. Basically, here's what it says. If a plus bi is a solution, so is a minus bi. Complex answers always come in pairs, conjugate pairs. If a plus bi is a solution, so is a minus bi. If a minus bi is a solution, so is a plus bi. It's impossible to have one complex solution. They always come in conjugate pairs. And that's why in Descartes' rule of sign, we subtract by 2's. Because they always come in conjugate pairs. Cool? All right. Now, we've talked about that before. And it's basically because complex answers come from irreducible quadratics. And all irreducible quadratics must be solved using the quadratic formula, which always has a plus or minus in it. So that explains why they occur. All right. Now, for this example, I'm just going to go ahead and apologize right now. It's going to be tight. I've already adjusted it for next year. I am so sorry. Do not write large. I'm going to do my best to squeeze it in there. This math has to think tiny, okay? And I also need to adjust the question to make it slightly better. I missed a word when I was typing it. I want integer coefficients, so real integer coefficients. I don't want fractions because that's no fun. I'm telling you that the zeros include -3, +2, -i, and y-intercept 0, -18. There. I realized after the fact that I wanted the question to be a little bit better. So I added a restriction. I gave you 3 solutions. -3, +2, -i. But because of the box, what else must be a solution? Come on, guys. If -i is a solution, what has to also be a solution? +i. Plus or minus I. They have to come in conjugate pairs. Think of this as being 0 minus I. That means 0 plus I also happens. So it's not possible to have just -i as a solution. You also have to have -i as a solution. All right? If you know the solutions, you know the factors. What you don't know is the vertical stretch or shrink, because it could have one. It doesn't have to, but it could. So I'm going to put an A on the front, because we don't know. But I do know if -3 is a solution, x plus 3 is a factor. If +2 is a solution, x minus 2 is a factor. Ew. I and negative I are also solutions. Ew. Do you know how you get this polynomial in standard form? What are you going to have to do? Multiply it all. That's lots of foiling, isn't it? I know, right? She says, oh, brother. Yeah, it kind of sucks, doesn't it? I can offer you a small shortcut. A small one. And that small shortcut's going to occur right here. Can we agree that this generates two solutions? Yes or no? Okay. A couple people said yes. Can we agree then that because it's two solutions, this generates a quadratic? Yes? Cool. Rather than go through the foiling process, I'm a big fan of rebuilding the quadratic that creates these imaginary solutions. And I'm going to do that over here. Time to rebuild a quadratic. Quadratics have what exponent? Square. So the first thing we're going to do is we're going to square both sides. Oh, I wrote it too. Don't tell the missus I'm writing in orange and green. She'll be mad at me. Because, ew, Miami. Now we have x squared. On the right side, I've squared a positive number and I've squared a negative number. Regardless, the result will be positive, won't it? So squaring actually eliminates the plus or minus also. I mean, in all actuality, the plus or minus occurred because I took the square root of a square. So squaring gets rid of it again. That's just going to leave me an I squared. That's not an I squared. But who can remember from earlier in the year what I squared equals? What is it, Alyssa? -1. So if you add 1 to both sides, what this gives you is x squared plus 1 equals 0. Which means these two multiply to give you x squared plus 1. And you might be thinking, wouldn't it have been just as easy had I foiled? And I'm telling you, for this example, yes. Foiling would have been just as easy. However, what if the example had been this? And I asked you to foil. Do you really want to go through that process of foiling? It's a nightmare. It's got foiling inside of foiling. It's awful. Or you could just use my method that literally I found when I saw this for the very first time in a book, and I was like, I'm never doing that. And I did it this way instead. So I said, okay, this is the result of a quadratic. Let me rebuild that quadratic. Subtracted 1 to the left. So now it said x minus 1 equals plus or minus 2i. Square both sides. Hopefully you know how to square x minus 1. Gets you x squared minus 2x plus 1. 2 squared is 4. I squared is -1. -4. Add 4 to both sides. Boom. Done. That's the quadratic factor, the irreducible quadratic factor that produces those two solutions. It's so much faster than this. When it's simple like this, foiling is just as fast. But you never know when you're going to need it for a more challenging question. Here, at some point in time, I am going to have to believe that you guys can foil some things, and you've started to see the patterns. again, there's not a whole lot of space. And at some point in time, I am going to have to hope that you can FOIL. So is it okay if I just write what this would multiply out to be rather than spend the time multiplying it? I mean, you guys know it would be x squared times x squared times 1, x times x squared, x times 1, negative 6 times x squared, negative 6 times 1. And you combine your like terms, right? Okay. All right. You'd have an x to the 4th, and there would be an x to the 3rd. Let's see, where'd my stuff from last period go? It gets you an x to the 4th plus x to the 3rd minus 5x squared plus x minus 6. So the 4 solutions get us there. All we have left to do then is to satisfy this criteria. If you plug in x equals 0, what is this going to give you? Negative 6. You needed it to be negative 18. So basically what happens is you do this. You go, okay, negative 18 equals a, and then you throw a 0 in for all of those things, and what you get is a negative 6. So what does a equal? Just positive 3. So the final answer is f of x equals, and then you have to distribute the 3, because it says in standard form, 3x to the 4th, I'm just multiplying all these by 3, plus 3x to the 3rd minus 15x squared plus 3x minus 18. That's beefy. We need more space for that. I'm sorry about the space. But would you like to ask me any questions about how it was done? Write the factors, FOIL where you need to, do all the distributions in like terms, and then ask yourself, if I plugged in a 0, what would this get me? Oh, to get me a negative 6. I needed a negative 18. Clearly a was 3. So if I put a 3 right there where a is and distribute it, distribute the 3 to all of that crapola, you'll get this. Yes? Why does it have it, you said? What is that? Because negative 3 is not imaginary. It only happens when they're complex. Okay? So if you have an imaginary component, they must come in conjugate pairs. Okay? Good question. And that leaves us just enough time to do the last example of the day. So Allie might want to unpack those notes. No, it'll be in the video though. We're going to do this one. So what do we see? We can see 3 solutions. And because we can see 3 solutions, we can write these 3 things out as factors. Now there might be, and probably is, a vertical stretch or shrink that I don't know. So once again, I'll put an A on the front. Since negative 2 is a solution, I know x plus 2 is a factor. Since negative 1 is a solution, I know x plus 1 is a factor. And since positive 1 is a solution, I know x minus 1 is a factor. But right here, my graph bounced. So what does that do? Puts a square on which factor? First one, second one, or third one? There it is, second one. Puts a square right there. This one doesn't say standard form, so let's just leave it factored. all we need to do now is make sure that that coordinate is respected. 0, 4. So it's the exact same thing we did on the last one. We're going to make sure 0, 4 works. So we've got a 4 equals a, and you put a 0 in all of these x's, and look what you get. 2, 1 squared, -1. Well, that gives you 4 equals -2a. So what does a equal? A is -2. So the polynomial in factored form is -2, x plus 2, x plus 1 squared, x minus 1. And no, the order of the factors doesn't matter. I know someone was wondering, but it doesn't matter. Thank you, nerds. That one was close.